Cameron Tropea from CU Darmstadt, a pioneer in experimental fluid mechanics. Professor Cameron Tropea, retired professor of fluid mechanics and aerodynamics at TU Darmstadt, Germany, earned his PhD from Karlsruhe University in 1982. His research spans optical measurement techniques, interfacial transport, atomization, and unsteady aerodynamics. Professor Tropea served as a German Council of Science and Humanities from the year of 2016 to 2020 and has been editor-in-chief of Experiments in Fluids since 2003. With an outstanding publication record, his work has been cited over 7,000 times. Today, he will speak on spray cooling, intelligent design. Let's invite Professor Cameron to talk.
Thank you for reminding me all of this. Thank you also for the invitation. And so I think a lot of people, you know me for doing very fundamental research. But actually today I'm not going to talk about fundamental research, but I say from physics to practice, practical research. And so already I anticipate potential for very high audience frustration because I'll show a lot of equations, but I won't derive them. So what I'm going to do is draw on a lot of our past fundamental work, use that work and just cite it and say, okay, what do we do with that work if we want to go to practice? And the other thing is that I think if we're going to practice, everybody should be willing to accept a certain degree of approximate solutions, not exact solutions. So what I'm showing you today is it gives you the trend, it gives you maybe the right dependency, but maybe not the exact solution. Huh? Okay, and it's about spray cooling. You've already read my title, so if I master this thing, it should go to the next one. And this is a really important slide because, you know, it says that I'm from the University of Darmstadt, but you notice a lot of this work is done in Madras. And I think Nairo is sitting over here, so he just got his doctorate doing this work. And so he's here, and the rest are this fundamental work that was done in Darmstadt on which we're drawing from to do this spray cooling work. Okay, so I said some take-home messages. So if you want to go to sleep after this slide. Okay, so can we predict spray cooling performance as a function of the hydrodynamic and thermodynamic quantities? And the other, the answer is yes. We think we can do that, at least approximately, and with some acceptable. And then the fun starts, because then you say, if you can do that, we could use that information to improve the spray cooling, or if we had a certain objective function which we wanted to attain, okay, how do we do that? I mean, what would be the Pareto curve to get us closest to that function? Okay, so that's the take-home message. This one I don't have to show you. You've seen it once or twice, I think, from several people. But obviously, cooling with phase change is better than without phase change, and that's the water spray cooling. So there's interest in that, and it's usually interesting for high flux densities, heat flux densities, and high temperatures. And the big problem is, of course, it's not easy to measure, and things happen at small scale, so there's a lot of empirical equations. And I think we've seen several empirical equations today, and everybody knows, be careful, just use it in the field or the range in which it was derived. Okay, so I think we can skip this. Susmita showed us a wonderful picture of the same. So everybody knows where you use spray cooling. And the idea is we need good models for it. So this is actually important because you've seen this curve at least twice today, but this is not the curve we have with spray cooling, because this is if you have pool boiling. We don't have pool boiling film boiling. We don't have film boiling in this sense because it's then sort of pool boiling. We never have above our droplets a fluid. It's gas. So our picture doesn't go like that. Our picture goes like that. So it's completely different than your normal pool boiling in film boiling regime. Okay, and this is actually, I have to actually work this thing. I could never get this to start on its own, and I don't know why, but we're going to accept it. This is now an experiment we did. I'm not going to talk too much about doing the experiment, but this gives you the thing we're going to talk about. And that is, first we heat up something to some high temperature. Okay. And then we say we're going to, so it's at some high temperature here. This is the overheat, or well, this is the actual temperature in that case. Then we start a spray, and depending on the distribution of drops, the number of flux and the size and all velocities and whatever, it starts. That was a hollow cone spray, and it starts to cool this thing down. And you can see if we took now a very high magnification of what's happening here, where it's cold, you're getting puddles. Where it's hot, film boiling, it's above the line frost, so it just bounces. It's the stove experiment at home. The droplet just bounces off. And so it's dry. Most of the time it's dry. In fact, even here, most of the time, most of the area is dry. And even here, there's still a lot of dry spots. Okay, so this was the experiment which Tensor did. And it shows, and so in time, if we continued in time and we looked at this position in time, it starts hot, it goes through some point, it goes through transitional boiling, and then it goes through nuke. So everybody knows this curve, but just time is going this way by spray cooling. Although it's a little bit different than if you're heating up. Okay, so the local cooling rate, and you can see it's local, it's different across the block. The local cooling rate will depend on drop diameter, drop velocity, number of flux, and of course the fluid properties. And so that's the problem. Let's go and look at if we can solve it. So this is the same curve basically. If this is the curve you just saw, this would be the temperature at any one point on that curve, and this would of course be your heat flux at any one point. And you can see in our case, somebody had that question earlier. The transitional boiling is rather short, actually. It's not in time, it's not a long period. And you might think, oh, maybe we can just forget that part. It's so fast, but it goes up sharply, so you have to take care of it. Okay, so I think this is, at least in this audience, doesn't need a lot of explanation. So we had these pictures, and again, we had one of these Questar long distance microscopes with high magnification, and so you could zero in on various short and see actually what's happening physically. And as I say, you've got a lot of dry spots, and I think if I push this, it goes on. And even in this area here, at this temperature, there's still a lot of dry spots in there. There's starting to be some puddles. This is what you have to capture if you're going to model this thing, which is actually very good for us, and you'll see that in the next few slides. So this is Fabian Fenzer. He did a PhD, and I think Peter Stefan mentioned you could download all the PhDs and launch that from some server. Okay, so this is what we take home from this, is that through most of the regimes, the surface is actually, small part is only being cooled at any one time, where a droplet happens to bounce off or stay. So now, I've called this intelligent spray cooling. I'm not too sure if it's intelligent, but okay, so supposing you could control drop size and drop velocities and number of flux. So it's clear you can't necessarily do those independent of one another, but supposing we got into the position we could do that, sort of a shower head monodispersed drop generator or something. And supposing you could do that as a function of time, so you could decide, as a function of time, these different things. So this is hypothetical, but nevertheless a good start. And then you could say, supposing you could also monitor the substrate temperature, so you could know where you are on the curve, so to say, then you could start saying, well, if I can do that, what's my objective function? And I've put down 3 or 4 objective functions, things you might want to do if you wanted to be intelligent, so to say, hypothetical. So one objective function is as fast as possible, cool down as fast as possible. Why not? That's a good. Or a controlled cooling rate, if it's, for instance, in metals, coming out of a rolled mill or something, the metal properties afterwards depends on the cooling rate and how long they stay at certain temperatures. So this is like quenching. And then one could be use as little fluid as possible. Why not? That could also be an aim. And that's the reason we did the work, because Satya Sheshadri, who was working on this with us, well, he's the one who has the project. He was with his organic. He was not interested in cooling. He was interested in vaporizing, which is roughly the same. The faster you cool, the more heat you get and the more vapor you have. So, okay, so any one of these, but I've decided to take fast cooling with minimum liquid. Supposing we wanted to do that. Okay, so we remember these, we have drop deposition, drops rebound, this is above and below line frost. So we could immediately have two questions that we would ask if we wanted to get this objective function. One is spend as little time as possible above line frost, and Sushmita said the same thing, avoid line frost. So get through that as quickly as possible. And what determines the heat transfer? Film boiling, so above line frost. And where's the line frost point? You have to know that. Okay, and the other question is stay as long as possible at critical heat flux, because there you have, and so you'd want to know what conditions must be controlled to maintain it. Okay, these are things, this is what I would say, if you could control all these things and be intelligent, let's do it. Okay, but now comes the practice, from the physics to practice. It's not as easy, and get through transitional boiling rapidly. Okay, these are single drop impacts. There's the nucleate boiling, watch carefully. The footprint doesn't change much. That's very important. Here's transitional boiling and film boiling. This is what we call thermal super repellency, or the Marilyn-Monroe effect. Lots of small droplets, and then it comes up and gets away from the surface. And Susmita showed the same thing, just a little bit faster. And this is, of course, the film boiling. It's that stove at home in your kitchen experiment. Okay, so we understand the physics, and now what we would want to know in each of these regions, which we go through in time, starting with the film boiling, we would want to know what heat does a single droplet take away. And we would say, well, if we knew the heat flux as a function of time and the wetted diameter, or at least the diameter of the drop, it's maybe not wetting in the film boiling region, and we knew the area, and this would be, this phi is sort of an oblique angle if there's some, okay, and you would integrate that over the, we'll call it the contact time, even though it might not make contact. Right? Let's just call maybe the residence time, or we'll use TC for now. And if you know that, then for each of these regimes, we would like to know the heat removal rate for each drop impact as a function of time, the area covered, and the contact time. And that would give us the heat removed per drop. Okay, then we know sort of, and then the probability, this is a little bit funny now, because now what happens is then one drop spreads out, another drop comes, spreads out, and they interact. And we did some wonderful work with Peter Stefan on that project, and you'd say, oh, maybe the heat transfer is not 1 + 1, but something less than 2. It's, okay, so you'd want to know that probability. Okay, but let's continue. We know it all. We simply know all of that. And now comes the frustrating part of the talk, because I'm not going to derive all of these things, but I'm going to cite literature in which it was very well derived and verified. So let's go. Please try not to get frustrated. And so the first one would be the film boiling regime, where it's sort of, you get this sort of pizza, and it's basically a one-dimensional heat transfer problem, because that thickness is typically 10 microns. And you've got 2 millimeters or something, so it's a one-dimensional heat problem, and it's done a long time ago. I mean, this is it's a very simple heat balance. You know the boundary condition here, you know the boundary condition here, the vapor temperature, the vaporization temperature, and then you've got the heat. This is latent heat of vaporization, and H is the thickness. Okay, so this is actually a well-defined problem. It's a one-dimensional heat transfer problem, and you can solve that. And that's the heat removed. So you can see the diameter, which you're spreading out, as a function of time, and you've got the heat flux here, and you go. This is the time it takes to go out. Now we do it. So I told you, please be prepared for approximate solutions. So we're going, okay, most of the heat is taken out during the spreading for 2 reasons. That's when you have the highest temperature difference and when H is the smallest. By the time it starts to come back, H is already bigger, the temperature difference is less. So we have a factor 2.3, I don't know, a small factor that we put in there. But it works well, as you can see. We get some predictions here, and we compare those. So this turns out to be the solution, and this is this factor. And it looks like there's all kinds of weird things in here, but it's absolutely correct except for that factor. So it's just those heat balance equations. And I'm leaving out all of the details. This is the frustration factor. Okay, so this is the dimensionless constant, accounts for later stages. It should be roughly 1. It's not 10, it's not 100, but it's roughly 1. And we fit it to experiments. And the experiments are wonderful. These were done, one was done, I think, in Hanover, and another, I think, by Specht. Where's Specht? Yeah. And so this is with no change of factor from our experiment. And I mean, take a look. The one spray is 18 microns at 27 meters per second. The other is 350 micron mean size. That means it works well. We're not too sure. Again, the experiments are not well described. We don't know, is it the mean? Is it the solder? Is it uniform across it? We don't know this. People don't always give you all the details. But in any case, we get very good agreement. So let's just put that and say, okay, we know the heat taken away by each drop from a single bounce. If we're doing trampolining, then we would do many bounces. And let's just accept that that's pretty good. Okay, now we go to the thermal analysis. This is the transitional regime, and this we call the thermal super repellency. And this is where basically what happens is you get contact, and Susmita showed it. You get contact when it comes down at that temperature, and then you get local boiling, little bubbles, they collapse, and you get these secondary droplets coming up. So you've had a mass loss, and they sort of disappear. And then of course you get the vapor, and the vapor, that's the Marilyn Monroe effect. Now the vapor comes up and throws up the ligaments, and it retracts from the surface. And this was done also some years ago, thermal atomization. And so the question is, do we know the heat taken away by each drop impact for thermal atomization? And the answer, of course, is yes. And these are very, very similar to what, these are typical examples from above, and of course we did from below with the infrared example, Boro from Peter Stefan camera. And I will maybe just skip this, but you can see this is breakup and atomization, and that's Leidenfrost rebound. And you can see, because you get a d squared, that's a Weber number dependence, because it's with u squared, du squared divided by, and up here it's not a Weber number. So okay, you understand sort of the difference between Leidenfrost and thermal atomization, where you get secondary droplets, and this was a little bit newer, so 21, and but in any case, so we have a little bit different dimensionless representation. And Susmita just showed you this part of the graph. That was one of her slides. She showed this coming down, and she had several different graphs in here. But you can see there's your nucleate boiling, there's your Leidenfrost. So we're looking at, the residence time. And in transitional, you're like this. So how long does the thing stay on the surface? So we needed that. That was the TC. Okay, so this is rather clear, and this is a little bit newer, this work here, but again with Benedict Schmidt. Okay, so that's transitional boiling, and now the interesting, we can move to nucleate boiling. So we actually know how much heat is taken away in the transit per. Problem, because we know the TC, but the problem is you've had some mass loss. So it's like nucleate boiling, because you touch down and you get the bubbles and whatnot. It's like nucleate boiling, but it's shorter time, and there's not as much mass left. And nucleate boiling is really easy because the droplet goes down, it stays there, and it all evaporates. So you know exactly how much heat is taken away. It's the late heat of vaporization times the volume of the drop. So easy. But of course, with transitional, you've had some mass loss. So transitional merges into nucleate boiling, so to say. Okay, and then you can measure this contact time. How long does it take? Because we know the heat taken away. That's heat of vaporization times volume. But how fast? That's more interesting. And that's the contact time. How long before I've called it contact time, the lifetime of the drop, that we should call it. How long does it take before it's all vaporized? And you can see we get this value minus 1.92 as a function of overheat here. And in Leidenfrost, of course, it's constant. It doesn't matter what the temperature, it just goes and it's constant. The rebound time, that's it's basically the time for the droplet to oscillate, which is, I think, an Indian did that, Chandrasekhar. It's planets, the oscillation of planets. Okay, so remember the footprint was constant for nucleate boiling. So we know the area, and now we have to work out the heat flux over that area for TC, which we know also it's TC, well, we don't know that yet, that was experimental. Okay, so you have a thermal boundary layer here, you have the heat flux density going into and you also have sensible heat, of course, and you have the wetted area is roughly d squared. We're going to make a fudge factor because the d squared, it's going to be proportional to d squared, but exactly, and the fudge factor is important because that will carry any influence of roughness or wettability, how much things spreads out. We're on a smooth surface for today, so we have a factor of, 2 something, and let's just accept that, but if you're going to extend this work to other surfaces, you might need a different factor there to take this wettability into account. So the total flux goes into drop, so we know the total flux. We know over the time what the answer is. This is what I said before. And this is also some years ago. Okay. So now again, the frustration factor, I'm not going to derive those equations, but they're done in that thing and we verify them and you get some solutions. So the scaled wall temperature and dimensionless contact time, and you can get from a lot of different authors or, I also had another one at different pressures. So it works very well. So again, I just simply have to say, let's not concern ourselves with details today. We're going into practice. Okay, so this is though very important. Now the question is, so we know how much, here's the film boiling, we know how much each drop takes away, here's the transition, we know that, here's the nucleate, we know that. But we have to know where are the boundaries? When do we stop film boiling and start transition? We have to know the Leidenfrost point. Okay, and so we can measure that. I mean, we do that experiment, we see where the curve goes up, and we know the point of minimum, so we can measure the Leidenfrost point for every condition we measure. So this is the Leidenfrost, I've called it temperature here, Leidenfrost temperature, but we like to say point because the temperature is different for all kinds of different conditions. We change the mass flux in the spray, we change the mean diameter, we change the impact velocity, we change the Weber number or the local Weber number. And you can see it doesn't change with any of those parameters. But it does change if you've got nickel or stainless steel. Then you get a change in the temperature. So what we're saying, and now if you start thinking about it, that makes sense. Because if you think, what makes that vapor layer? The vapor layer is created, how fast can heat get out of the material? So it's the effusivity. The effusivity is the important parameter. And because that tells you how fast you can remove heat. And so here, the Leidenfrost condition is actually a very strong factor of the effusivity of the material. And this is then the delta T, so the superheat necessary. At that delta T, you have the Leidenfrost point. And you can see it's a weaker it works out actually very well. And this is also, that's the film some years ago. Okay, so let's summarize where we are. We have film boiling, transition boiling, nucleate boiling. We know the time, the TC, we call it TC mostly. We know the areas roughly. We know the heat flux roughly, so we know for every single droplet how much heat is taken away depending on which area we're in. So now we go and say, well, if you remember the movies, most of the time everything was dry. So immediately you think, oh, let's do superposition. Let's just add up all the droplets, and which you can do. And you get this sort of, superposition. And then you add them all up and you get some sort of a, you could turn it into a heat transfer coefficient if you wanted. But I think don't worry about that. Just measure the heat removed. And, so this is the number flux. This is the heat removed for every single droplet. And this is your delta T. So this is a very simple equation. It's sort of thermal heat transfer 101. And the number of flux is then very important. How many, and in this, of course, is all the rest of the, how big is the droplet, how fast was it, and all these things. Okay, and then you do some, now comes the trick. Remember, I said, maybe you get some drop-drop interactions. What's the probability of drop-drop interactions? This is actually a Monte Carlo simulation. Some have are just hitting or just bouncing back, some are a little bigger, and occasionally there's some drop-drop interactions. So we have we've called it the wetting ratio, okay? So it's basically the actual covered area over the cumulative. So if you just did superposition, you had n drops, and each one covered this area, then n times that area would be the total. But if they're intersecting, then it's a little bit less. That's the little bit less. So this is less than 1. Is always less than 1. The question is how much. So as long as it's near 1, superposition holds. If it's a lot less than 1, probably our answer is wrong. Because we don't really know too much about intersecting drops and the heat transfer. Okay, so if we that would be taking drop interactions into account. We assume that the heat flux is less than 1 plus 1. And the estimation we want to estimate what is the flux. So now we use simply, of course, the Poisson distribution. It's a random process we assume and just work it out as a Poisson process. But if we did get this, then we would just say, let's scale the heat transfer with something less than 1 because it'll be a little poorer than if every drop made a contribution. Okay, so the implicit assumption is that heat transfer scales with the covered area. Okay, again, I have to appeal to you, accept a little bit of approximation here. It might not be exact. So this is actually together with Peter Stefan. We did this once, but this is like one single case. So we okay, 2 drops come down and they merge, and if it's a little farther apart, they don't merge much, and if they're closer together, they merge more. And then you measure the heat transfer compared with 1 plus 1, and it's less than 2. And okay, but then you have to also consider maybe one comes first and the other one comes later. And okay, we haven't done that. So if you're looking for a good dissertation, there's lots of work left to do. Okay, anyways. So, you have this sort of ideal case, there's some separation that come at the same time, and sure enough, you get something less than 1, and if the separation is farther apart, it's not much less than 1. If it's closer together, then you get it much less than 1, and it's rather, this is not rocket science, but it's good science, I would say, and this was some years ago also. Okay, so our estimation is, let's just use the effective area. What did I do there? Effective area. So assuming impacting drops are completely random in space and time, then we use the Poisson distribution, where of course your lambda in the Poisson distribution is the average number of drops per area. And we can know that because that'll be dependent on the number of flux, the diameter, and the velocity, because the velocity determines how wide they go, and then the number of flux how often, and then you just use that in your normal. And of course, the probability that you get more than 1 at the same place on the is exactly 1 minus the probability that k is equal to 0, and k equal to 0 is really easy to work out. So you know exactly the probability of interaction. And so you can work out that eta turns out to be an easy number as long as you can compute that. But that's Now comes the practice part. This is the part that Naila and I worked, I think, several months on. How do you get then the number flux? Because if it's a flat plate and everything's coming normal, no problem. Now what happens if you start going to more complicated geometries? You know, you have to cool maybe inside a cylinder or something. Okay, so this is just an example of this eta. We say if it's 1, we think everything's okay. If it starts going less than 1, maybe our solution effective covered area is not the best. But this depends a little bit in your spray on mass flux and things like that. Okay, and drop diameter. And it's clear as the drop diameter gets larger, the probability of interaction is higher, and then your eta gets lower. So, okay. Yeah, fairly straightforward. So now comes this challenge. So I always like to use this analogy. You're driving your car in the rain, and your back windshield never gets wet, right? Because your back windshield is like this, and you're driving, so the effective velocity is parallel to the windshield, and the number flux, that's a vector. Flux is a vector, and the vector is the normal to the surface. So the number flux is 0. Okay, so you don't get, your back windshield shouldn't get wet. So now you start looking at things like this, which is what we were doing with cylinders. And then it's clear, along here, the number flux might not change too much, but along here, it'll go to 0 at the edge because they're just glancing off the surface. So then you have to start doing some vector algebra and work out, okay, what is the effective number flux? If you know in the spray cone what, the droplet size and velocities and number flux locally, then you have to say, and that's hitting some surface, and then you have to work out the local number flux, because that's an important parameter for all of these things. It was in the heat transfer coefficient. It's in the alpha. The lambda of the Poisson distribution. So you have to work that out. And so it sounds easy, and I hope I made it sound easy, but it does take time. It's definitely one dissertation. Okay. And so you could see, for instance, this is a complicated diagram. So this is eta. So if it's 1. This is lambda to lambda max. So lambda max is here, and if it's 1, you're out at the edge here, and if it's 0, you're in the middle. And this is then for a given diameter and whatnot. This one is you're moving along here or you're moving along here. So one is moving along there, and the other one is moving along there, and you can work out this eta. But all I'm saying is that's the arithmetic you have to do to get to carry on. So then you have the regime boundary. There's the film boiling to transitional boiling. This we're taking from our previous work. That's Vaderu. And transitional boiling to nucleate boiling. We have that. It's basically when the residence time of the transitional boiling approaches the residence time of the nucleate boiling, and then that's it. You're not losing any mass. Those are secondary products. Okay, so and then you can do some verification, which we did on the tensor, and this is what we get. So the red line is the tensor work. The dots are the tensor work, and the red line is our computation. So this is transient spray cooling, and we're getting the transitionals correct. The limitations correctly, and okay. As I say, it's not exact, but it's not bad. So now the fun starts. So you've got this tool, and you say, okay, we can believe it, and let's see, if we change different things, what happens? And so, you can. This is rather good work. This is things like, so this is for certain data numbers, we change the velocity and how this cools work. It starts at a high temperature, goes through film boiling, goes through transitional boiling, gets into nucleate boiling, and then eventually is cooled down. And you can see, okay, how do things change with velocity, or how do things change with the mass flux in the nozzle if you assume everything is uniform in the spray cone, how do things change with diameter. So now, okay, these might not be exact temperatures, but you get the dependencies, and you have a feeling, now I understand it. And some are non-intuitive, by the way. I'm not going to describe some of those, but sometimes you look at it and say, why should this one the bigger droplets be slower cooling down than the little droplets. And it's not immediate obvious because the bigger droplets would have a bigger area. They should take more at a time. But for the same mass flux, remember, the number of droplets will go d cubed. Same mass flux in the nozzle, and you go smaller droplet, you have a lot more smaller droplets. And remember, the number flux was an important parameter. So it's not always intuitive. And this is what I think is rather valuable now at that point. You can start seeing these hidden dependencies or interactions. And this is now this we did just for the sake of a lot of people who I think don't do things properly. You know, you get all kinds of publications. I changed the height of the nozzle and measured the heat transfer rate. Who cares? It's not the height of the nozzle that's important. It's the number flux, the velocity, and the droplet diameter that's hitting that local position. That might be a function of height, but that's not the main parameter. Okay, but so we said, okay, if we kept everything constant and changed the height, of course you get exactly what you expect as you change the height. If you go up higher, then it takes longer to cool because the number flux goes down. Okay, for the same area. Okay. Actually, I'm going to skip over a few of these things because I think I'm actually finished. I basically told you what I wanted to tell you, and you can carry on and do all kinds of different things. However, there is one more slide, and so we started looking at different effects. But there's one more slide I would like to show, and there's a little story behind this one more slide. And I think, just a minute. No, I didn't put it, sorry. And the story behind was that Marco heard something similar in ISC a year ago, roughly. And he asked us, but the mass flux you should non-dimensionalize, which we did. And the question is, if you wanted to non-dimensionalize mass flux, how would you do it? With what quantity? And it's actually quite simple. You for a given diameter and spray cone angle and area, you would say, what mass flux would you have if all of the droplets spread out to the same area you're cooling? That would be, then you would have mass flux 1. And usually you have something less than 1 because there's dry spots. Okay, sorry I didn't put it in, Marco, but we have that. But I did have one last, because this last one is also just, it's not published or anything, it's just new. You hear a lot of times, oh, if you had intermittent spraying, it could be faster. Why? Because, I mean, okay, this again, non-intuitive. Supposing you said, oh, intermittent spray could be faster. Why? Because when you stop spraying, then the surface temperature would heat up. And when you start it again, you'd have a higher temperature difference and you'd get higher heat transfer. Don't worry about that. It's not going to be better. It's always going to be worse. And we're just working on exactly the conditions where that's going to be worse. But and this is a good example, depending on the duty cycle. This is the continuous and this is the intermittent. It takes longer to get to the same temperature. And this is where that was film boiling, this is nuclear boiling. This is unfinished. All I'm saying is that now you have a tool to play with these things and try and work out, what might be better or worse with some degree of reliability. Thank you very, very much for your attention.
I have a question on the intermittent, because have you investigated all the different intermittency parameters like the spray duration, pulse width, and so on?
Even yesterday we were talking, so we're working on that. We might find an intermittency duty cycle that works better. We might.
Because as of now, it seems that it is not as good as continuous spray, but there may be a potentially.
Yeah, but I think it depends a little bit what conditions you say. So let me say where I think it might be better. So if you had a certain mass flow rate through your nozzle and a certain number density, and you said, I'm just going to turn it on and off, that's going to be worse than continuous. I can tell you that's what we did. But if you said, I'm going to turn it on and off, but change the mass flux so that the same mass went through the continuous, then it might be better. I was going to write him an email last night, but we'll do that in the next day or two. Yeah. And then it could be better, but then you're changing your mass flow rate.
Exactly. Then it's comparable mass flux for
so it's a little bit, you have to control your pump then.
Yeah. It's something that we are thinking about.
But that could be better. You're right. But okay, all I'm saying is now we have a way to check it. Didn't have that before.
Okay, Monu, don't start experiments before knowing this.
Wait for the result,
But it's too late. We already
It's too
got
late
the
now.
design.
It's
We
too
have the
Let's try. Okay, we are going to validate.
So, Cam, you made the assumption that all your liquid is reaching the surface, right? And we know that's not true because, I mean, we do experiments with paints and we know something like almost, up to half of
overspray.
it is not going to reach that. And when you change your droplet size distribution, so the sort of thought experiment you're doing where you make the droplets smaller, because at one time we said if you make your droplets infinitely smaller, you will get a perfectly even paint spray, except none of your droplets are going to reach the surface.
That's correct.
And so how do you, when you're comparing it with experiments, do you account for that, or how do you deal with that?
Yeah, but it's a great question because obviously overspray is rather important. And by the way, wind drift also for agricultural sprays.
Yeah,
is the
that's what I'm
same.
saying. That's
And overspray
all of-
transfer
all of those. So
efficiency.
when you change your size distribution.
No, this was my appeal to accept that it's not exact and we're just approximating things. But we have a condition where, and by the way, so it's actually a good way to, in these cases, for instance, we've made the spray cone angle, maximum spray cone, is such that the last droplets just hit tangentially. So there's nothing that goes beyond the cylinder. But this is something you could easily program into you could take into account, you're spraying this plate, your spray's up here and some of it goes over here and never hits the plate. Okay, you can take that into account in the program. That's not a problem. But you're right, and what you mean is overspray through induced convection, this we don't account for.
It's also smaller droplets don't have enough momentum to actually get through the boundary there.
But this is another really important point which I skipped over, because what we did is then we said, suppose we made polydispersed and monodispersed, and then we said, if you had a polydispersed, would it be better to take the mean or the Sauer mean? And the Sauer mean in fact gives you a better answer. The difference here is smaller than the difference here. And the other thing we did is, and I don't think I put it in here, is so this is transitional and film voiding. So now what we did is we said we had a positive correlation between size and velocity, or we had a negative correlation. So just to make it clear, if you were spraying into ambient, the big droplets would be going faster than the small droplets. They would slow down faster. So big droplets are faster. That's a positive correlation. But if you're injecting into a fast-moving turbocharger or scramjet, the little droplets would accelerate faster. Small droplets would be faster. You'd have a negative correlation. So we did the positive correlation and the negative correlation with a log normal, with some Umax and Dmax and whatnot. And it's always the case that your positive correlation is worse than your negative correlation. But then it tells you the best thing to have is a bunch of really small droplets going fast, which is what you said. Infinitely small, going really fast, and they all hit the surface. That's the best heat transfer you can get. And when we were doing the Gesenkschmieden, what's that, hot forging, and we were working with them, basically the idea would be have a big room, make it full of fog droplets, and then blow it at the surfaces, and that would be probably the best solution, but it's completely impractical.
Time for one last discussion. Time for one last question before we break up for tea.
We have two.
Okay. I tried to answer one of your first aims or questions. You said you want to have a maximum fast cooling with as little as possible liquid.
Yeah.
And I think I can't answer this.
No, I didn't. All I said is if you asked that question, you would have got those two questions to. If that was your objective faction, you would have had two questions to answer.
It's two separate questions.
Because would get fast through transitional, and sorry, fast through transition or little possible time in Leidenfrost, yeah, I mean, but I didn't try to answer those.
As little as possible liquid, because
Yeah, and I didn't even answer that question. But all I said is those are the sort of questions you could pose and now use the tool.
there should be an optimum somewhere in between, because if you have very high mass flux, then you flood the surface.
Listen carefully, Marco.
This is what,
Carefully.
this is
This
what
could be
is
the
happening.
extension of the work we're doing now.
Because
And if
with
you
the,
reduce the mass flux, then it should get better and better up to a certain
up to a given
and then-
point.
Exactly.
And also, for example, using air assisted atomizer. So where the air can push back, no? We are coming to
So
some
we
Gilles
cannot,
comments.
we
So
cannot capture that, but if you could work out the numbers, you could use it. So this is, actually, the question is great, because it says that's exactly what we want to try and do with the tool. And that's the practice part, physics to practice. And it sounds simple, but it took a long time to get this far. But okay, Marco, this sounds like some interesting.
yeah.
Okay.
Okay, so I think let us thank the speaker.
The engaging session. I request Dr. Samidi to present the book.
We're trying all permutations.
Where do we put this?
We don't want to involve participants.
So,
We don't want participants.